Here's a really important definition. A subgroup H of G is a normal subgroup of G, emphasis on the word normal, if, kind of fun here, A equals ha for all A and G, right? The left coset of H and G containing A equals the right coset of H and G containing A. A equals ha for all A and G. That's the definition of a normal subgroup. It's not telling you why normal subgroups are important, but they are extremely important. This is a fundamental thing to learn in group theory. Notationally, when you say H is a subgroup of G, so far we've always written this kind of thing. And we know, remember, we don't say less than or equal to, we say H is a subgroup of G when we see this kind of thing. When H is a normal subgroup of G, we write this a little differently. Most people write it as just a single triangle like that. Though, if you want to emphasize that H could equal G, you could write it with a triangle and a line under it like that. But most people just default to just a single triangle. And it's technically, if you want to be picky about it, it's an isosceles triangle where sometimes people make the congruent sides a bit longer than the other side. Okay, it's a stylistic thing. It doesn't matter. That's the symbol for H being a, not just a subgroup of G, but a normal subgroup. Normal subgroups are subgroups. You have to have a subgroup to begin with to call it normal. It should be immediately obvious from this definition. An immediate fact that follows. You could call it a corollary of the definition. That's never, the word corollary always goes with theorem, but it's almost like it's such a quick fact. It's almost like it's a corollary of the definition, is that if G is abelian, every subgroup is normal. Every subgroup of G is a normal subgroup of G. So this is only more interesting, you might say, when G is non-abelian. Though we still think about normal subgroups plenty of times when G is abelian. It's just easier to think about in that case, because it's immediate that the subgroup is going to be normal. Just like there's a subgroup test. Well, we saw 3 subgroup tests, right? The one-step subgroup test, the 2-step subgroup test, and the finite subgroup test. We almost always use one of the first 2. Just like there's a subgroup test, there's a normal subgroup test that says if H is a subgroup of G, and, okay, let's phrase this differently. Suppose H is a subgroup of G. It's the theorem. Normal subgroup test is what it is. Suppose H is a subgroup of G. Then H is normal in G if and only if XHX inverse is a subset of H for all X in G. And in fact, you can say a little bit more than this. This if and only if can actually be continued to say XHX inverse actually equals H for all X in G. Kind of amazingly, this thing is a subset of that thing if and only if it equals that thing. That like hardly ever happens in set theory, right? Unless you have some other reason for it to happen. Well, this is one example where there's another reason for it to happen. But as far as proving that H is a normal subgroup of G, you only need to prove this set inclusion. that's good enough. We have encountered this thing before. What is this? That's called a conjugate of H by X. What is it? What's it defined to be? It's the set of all elements. I hope you could guess what it's going to be, of the form X times little h times X inverse as little h varies over capital H. Back about a month ago, we did verify with a subgroup test that that's a subgroup of G. We did that in class. We used a subgroup test to verify that this is a subgroup of G. No matter what, no matter whether H is normal or not. Being normal, though, means it actually, in the end, actually equals H, no matter what. Kind of a weird thing. You can imagine this to be G and this to be H. In general, when you form these conjugate subgroups, X, H, X inverse, you could get something, it's going to be a subgroup of G, but it could be something different. Maybe it looks like this. There could be some overlap. In fact, there's got to be at least one element that overlaps, E. Maybe that's X, H, X inverse. Maybe it's different than H. If it is different than H, then H is not normal in G. Right? This is an if and only if. You could negate both sides, and that would be a true statement as well. H is not normal in G if and only if this is not true for some X in G. For some X in G, this is not a subset of H. That would be equivalent to H not being normal in G. So if the picture really looked like this, that would be a situation where H is not normal in G. I suppose we could write a triangle with a slash through it if that were the picture. There was some X where that was the picture, then H would not be normal in G. But if for every X, and who knows where X is, X could be over here. If for every X, this conjugate subgroup actually, in the end, equals H, that will mean H is normal in G.